Okay, so my name's Drew Henry, and this is a video extra credit for my Physics 2211 class, and today I'm analyzing the physics of a video that was posted on YouTube. It's called The World's Largest Rope Swing, where a group of people went up and made a rope swing at Corona Arch in Moab, Utah. So here goes. For the first part, I was asked to find the velocity when the rope catches at the bottom of the swing. And that, start off, we're assuming we have an ideal rope, which isn't going to be stretching, or it's going to stay the same length, which they listed it caught about at 130 feet, which is roughly 39.6 meters. So, the method I chose to solve for this was using the energy principle, which states that change in potential energy plus change in kinetic energy is going to equal the total energy. Now I assume that the system was everything, the whole universe, so we can assume that there's no work acting on the system, so therefore energy isn't going to change at all. So since we're assuming that, the potential energy plus the kinetic energy at the first height is going to equal the potential energy plus the kinetic energy at the second height. Now, since the kinetic energy at the beginning is going to be 0 because the velocity is 0, we can just go ahead and knock that off. So then solving for velocity, we cancel the masses and we get the velocity at the bottom of the swing is equal to the square root of 2 times the acceleration of gravity times the change in height, which that'll be the length of the rope. And so plugging in our numbers, we get the velocity at the bottom of the swing is equal to 27.06 meters per second, which is pretty fast, so it means it's fun. And for the second part now, I was supposed to find the force of tension at that point at the bottom of the swing. So now the force of tension will be equal to the perpendicular force of net force. And the forces we have acting on that are the force of gravity and the centripetal force, which the centripetal force is equal to mass times velocity squared, all divided by the radius of the kissing circle, which again is the length of our rope. So, plugging in our numbers using the velocity from before that we just solved for and the length of our rope, we get the force of tension is equal to 1986.37 newtons. Now, there's going to be a little twist, and we're going to solve for the tension and the velocity at a 30-degree angle. Now, this will be slightly more difficult because force of tension isn't in line with the force of gravity. So, we're going to put the force of tension going in the y direction and the force of gravity going off into the negative xy-ish direction. So, using the energy principle again, we solve for the velocity. Now, at this time, we do have a kinetic energy that we're comparing it to. We're comparing the kinetic and potential energy at the bottom of the swing with the kinetic and potential energy at that 30-degree angle. So, we can cancel masses again, and then solving for velocity at the point at which the swinger is 30 degrees from the bottom of the swing. We have the velocity at that point is equal to the square root of velocity at the bottom of the swing plus 2 times the acceleration of gravity times the change in height. Now, you notice we have the change in height, plug that in as negative 17.42. Maybe asking how I found that. Well, if you go back, I use the sine of 60 to times the length of the rope to find the distance from the top of the arch that the jumper will be at the 30-degree point. And then I subtracted that subtracted the length of the rope from that in order to get that negative 17.42. Now, plugging those numbers in, the velocity we had from before, acceleration of gravity, and change in height, we have velocity is equal to square root of, well, skipping all that, velocity is equal to 19.77 meters per second, which that's going to be more correct. Well, not more correct, but it's a reasonable number because it is slower than the velocity that we have at the bottom of the swing, where we have more time that the force of gravity is acting on the swinger. Now, calculating for the force of tension, we have the same equation we used before. Force of tension equal to the net force of perpendicular to motion, and that's equal to the force of gravity times or plus force of the centripetal motion. And now we're gonna multiply the force of gravity, since it's not in that same streamlined direction as the force of motion. We're gonna multiply that. Well, it's not perpendicular to the momentum of the object, of the person. We're going to multiply it by the sine of 60 in order to compensate for that and to find the force of gravity in the perpendicular direction. So plugging those numbers in, I did wind up messing up there, believe it or not. That shouldn't be 27.06, but it should be this velocity right here that we saw for 19.77 meters per second. And solving for the force of tension, plug that in. And let me just make sure real quick that that number is right, because I'm pretty sure I used the wrong velocity, but we'll double check. 9.8 times 70 times the sine of 60, that plus 70 times 19.77 squared divided by 39.6. So yeah, that number is wrong. It should be 1284.99, which again seems more reasonable compared to the velocity that we got and the force of tension we got before. Now for the fourth part, we're going to take into consideration that no rope is going to have zero stretch. There's always going to be some stretch to that rope, because pretty much a rope is a series of springs lined up in the intermolecular level. So we're going to look at it as a spring. And I was looking up online and seeing that the about round average spring stiffness of a climbing rope is about 2,900 newtons per meter. Now, plugging that and the force of tension that we just solved for the force of tension we solved for at the very beginning, because we're calculating the change in length when the person is at the very bottom of the swing. So, plugging those numbers in, we get 0.68 meters, which isn't too much, but it's a good bit. So you really, when they were making the swing, they had to keep that in mind, that the rope was going to stretch. Now we're going to reapply the angle using the angle. And so plugging, I'm going to use the number that we realized was correct, since I messed up on the earlier slide, believe it or not. So if you don't remember, that force was 1,284.99 newtons divided by that 2,900, and all the way to the 0.65 there. The actual stretch when the jumper is at a 30-degree angle is going to be 0.44 meters. Alright. Hope you enjoyed my video, and go do something fun.